Okay, welcome everybody. It's a great pleasure to introduce today's speaker, our very own Professor Matt Hitchman. Matt received his PhD from the University of Washington in 1985 under the mentorship of Conway Leobi, whose, Grant can attest to this, whose first year dynamics course was notorious and intimidating, even though he himself was, like Matt, engaging and extremely amiable as a lecturer. So I don't really understand how that reputation was earned, but everybody was nervous about that class.
He would just kind of start and go like a machine.
Yeah, he was something else. He was something. But if you stopped him with questions, he was more than happy to answer them. But upon graduating, Matt stayed for some part of 85, 86 as a scientist. I got there in March of 86 for a few months and then came back at the fall. I don't think we crossed paths, but if we did, it was cursorily.
I had to leave because I was tired of losing the forecast contest.
And then he ended up at NCAR, where he was a scientist for a couple of years through about 88, and then 30 years ago, this fall, joined our faculty as an assistant professor and then was full professor by 1996, so went through that quickly. And then, as is often the case, he was immediately drafted upon becoming full professor to be chair. And he was successful at that for 3 years, served the department really well, and remained enviably productive and influential as a scholar and a mentor. He graduated 4 PhDs by 2000 and then 4 more at least since, and more than 20 master's students over this period of time. And he's published on the order of 60 or so papers on a wide variety of topics ranging, and they're really wide. That's the thing that strikes me looking at that resume, Matt. It's really remarkable. They range from East Asian cold air outbreaks, ozone in the stratosphere, equatorial tides, gravity waves, inertial stability, wave breaking, climatologies of a host of things, the Aleutian high, stratospheric aerosol, wave breaking along the subtropical tropopause, the QBO, and then I haven't covered it all, but today we're going to hear about the formation and vertical structure of upper tropospheric, lower stratospheric jetlet, and potential vorticity dipoles. So, my friend and great colleague, Matt Hitchman.
Thank you, John. That's very nice of you. Yes, I guess I have the temerity to try to delve into tropical cyclones, which everybody likes them. I guess I'd have to go back to, I did take a class from Bob House, so maybe I owe it to him. It just sort of an intrinsic interest in how do clouds work? And how do they work collectively in mid-latitude and tropical cyclones. So this is about the formation of jetlet PV dipoles near the tropopause, within 2 kilometers above and below the tropopause, and we call that the upper troposphere, lower stratosphere, or UTLS. And here are a couple of examples. This is potential vorticity. The E part is just equivalent PV, and it includes moisture, but at this level, we're talking 4 parts per million, so it doesn't matter. PV is what this is. And there's a low pressure center here in tropical cyclone Talus, and it's approaching Japan, so the air flow in mid-troposphere is this way. But at upper levels, you know, it's anticyclonic, so the shear is this way. And we have a low PV member of a dipole just on the radially outward and on to the left of the shear, which is southward. Do more of that in a minute. Here's an example from the mid-latitudes, 3 updrafts here, and a couple of dipole pairs, maybe 1, 2, 3. And again, the shear is oriented this way. It's a very deep, tall shear, goes into the stratosphere, but these thunderstorms punch into the base of the stratosphere and stop. Well, again, this is negative potential vorticity. We have anticyclonic flow around it. It's inertially unstable. And it lies to the left of the wind shear. So part of what we're trying to do is to develop rules of thumb that can sort of simplify things. I try to take a reductionist point of view. The idea that one should eschew sesquipedalian peregrinations, something like that. Occam's razor.
Is there a way to see the wind shear on those plots?
No, I have some other ones where I doctored it up with an arrow, and then I have some profiles that we can look at later on too, to show that. Okay, so hopefully, well, most of this is new since June, so hopefully you'll find it interesting. I know I've given some talks on this general topic before, but just to expand this out, what is UTLS? The upper troposphere, lower stratosphere. And we're talking about jetlets that always form with a dipole. If you form a dipole or a pair of counter-rotating vortices, you have a jet. And if you have a jet, you have a dipole. And we're talking PV dipoles. They're closely related to dipoles of absolute vorticity, just modified by 1 over rho d theta dc. Incidentally, that factor gives you a boost of about a factor of 20 in going from the mid-troposphere to the base of the stratosphere. Just 1 over rho d theta dc gives you So the basic question is, how are these things formed? And why are they sharply concentrated in UTLS? If you look at PV structures in updrafts, they're highly variable. Sometimes you see the classic vortex stretching up to the heating maximum and the PV is generated positive, and then compression in the updraft portion that's approaching the tropopause, you'll see PV negative, but it's way more complicated than that. In the troposphere, it's really hard to sort out. But a very striking, reliable signature is right in the UTLS. When an updraft hits the base of the stratosphere, you get this dipole that's very robust. What is their vertical structure? Not just in the UTLS, what we found is that they're connected intimately to a boundary layer flow. A tilted updraft then gets ejected poleward and joins the extratropical stratosphere, the subtropical westerly jet with material flowing right into the extratropical stratosphere. So there's a very interesting vertical connection. Further, the updraft is intimately linked to one phase of a gravity wave pattern. It exactly fits with the updraft downdraft pattern. So we'll look at the 3D structure. What is the role in exciting gravity waves? This is a topic from applied mathematics in the mid-aughts, and I'll start with that. And then, can their form be predicted? And by this, I mean, can we come up with simple rules by which we can understand which direction is the jetlet and why? And will there be a jetlet? And if there's no jetlet, we won't have a dipole. So what I'll be advocating here is sort of a transition from the theory that these are best viewed as an updraft tilting pre-existing horizontally oriented vorticity, which is still a robust idea, but I'm going to suggest that a more intuitive, easier to grasp physical mental model is the difference in the momentum in the updraft compared to the air that it's being ejected into. A very simple idea. And I think that will help us be able to predict the form of these things. Okay, here's an outline. I'll start off with some examples of tropical cyclones, and there'll be a quiz associated. Which one is it? Then we'll get into the theory of PV dipoles being formed according to the theory of Chagnon and Gray by an updraft simply tilting pre-existing vorticity. If there's some, let's say there's shear that way, then the vorticity would be oriented that way. And if you have an updraft, it'll tilt it into a horseshoe shape, just like for the theory of how an outflow boundary layer can be tilted upward by an updraft and maybe form a tornadic vortex. So it's analogous to that theory. We'll briefly look at the mid-latitude cyclone Super Tuesday to see if the rules work for that. And then a series of tropical cyclones, Talus, Edouard, Eta. This one's from the southern hemisphere, so anomalous PV is actually positive. But we'll see how the rules work for the southern hemisphere. And then, can the form of PV dipole jetlets be predicted? And if we have time, I think we will. This is about a 50-minute talk. I'd like to show some examples of sheared convection and then talk about momentum transport. See what you think of that. I'm trying to make progress toward better understanding. All right, so here's your tropical cyclone quiz. And in the back of my mind, I'm thinking, how common are embedded convective complexes? So this is the question I'm asking myself. The whole paradigm of tropical cyclones is that they are fundamentally a shield shape, that they're axisymmetric, that you might have some spiral rain bands and they always contract and rebuild the eye wall, and there's this kind of theory of eye wall replacement, and they're basically axisymmetric. Well, kind of, but maybe not. So let's see what you think. All right, what's this one? Which hurricane is that?
Oh, I know that. Galveston. That's the
Galveston 1900. Maybe, I want to say August 23rd, because there's 4 other August 23rds here. But I think it was August 27th, so that's cheating. How about that one? This one is a Category 5, Andrew, 1992. Good. All right. How about this one? This looks sort of vaguely like Louisiana.
Yeah.
Katrina. This is maybe August 23rd, 2005. Right? I think it was maybe down to Cat 3 at that time. I'm not sure. This is also from August of 2005. And it was touted as the Wilmette, the most potent tropical cyclone ever in the Atlantic. And I don't know if that's measured by maximum wind speed or minimum pressure or both. I'm not sure.
Minimum pressure.
Minimum pressure. And it took a long track past the Yucatan and then veered across Florida. And I kind of like this one because other people have noticed this. In the subtropical westerly jet, you get spotification. And around tropical cyclones, you get that also. So I know Greg is interested in that. And basically what happens is you all these individual convective elements are exciting gravity waves, and there's sort of isotropic illumination of all these gravity waves going upward. But there's a selectivity based on, well, it's a theory by Dunkerton and Butchart from 1984, that if you have isotropic emission of gravity waves and you have shear, the ones that emerge after propagating through the shear are the ones that are going against the flow. So the individual phase surfaces are propagating upstream as this anticyclonic outflow occurs, and it's a pretty common feature. This one, this one's in the Pacific from this year.
That's the one that hit Hawaii or something.
Oh, yeah.
First letter?
First letter is L. It marauded, it harassed Honolulu, but never really quite delivered. Lane. Yes, it's Hurricane Lane, and it's a nice space shot. I think that's the International Space Station appendages there. Kind of a little bit of spokification, you can see. This one is Typhoon Trami that traumatized Japan. This is the day I landed in Japan when I went there a couple weeks ago. And it was meandering around through here, and then all of a sudden went straight toward Japan. So the next day at noon, they closed Starbucks everywhere, and everybody's getting stuff in, they were all buckled down. But that night it was only 35. That's the only typhoon or tropical cyclone I've ever been in. And it rained and it was dark. It was really wet and warm and rainy, but it only got to 35-mile-an-hour gusts that day. I thought maybe Kyoto's surrounded by mountains, and perhaps historically that's why it gradually sort of prevailed over 1,000 years. But and it did turn out that in Tokyo later that night, some people were stuck in the airport in Narita, and other people who lived in Tokyo said, yeah, it was 95-mile-an-hour gusts, and there's no mountains to the east. The track of the low is up the east coast of Japan. But so a couple days later, I took a hike up the Daimanji, which is, they have a clearing on the mountainside near Kyoto, and they built the structure in the shape of the Oki symbol, which is shaped like that. And this is one leg, and in October, they light these fires. You can see their space like that. And so from all over the city, you can see this beautiful lit figure, a big sign, Oki. Well, this is the way I usually go down, and it's kind of a dicey ravine, but it was completely filled with these beautiful trees. These are like this big around, perfectly straight, really smooth. They used these to build the temples, and it's some kind of relative of redwood or sequoia, I think. Really nice trees, but hard to get through there. And I thought, that didn't happen from Trami, and I realized, oh, well, Kyoto's not that protected. All these trees got wiped out. It was early September. It was, which one was this? This one was Typhoon Jebai, which made a much more direct hit on southern Japan, just kind of ground its way right over Kyoto. So it depends on the angle. And I think the mountains helped Kyoto, but not always. Oh, it's this one. So this is all chronological. This is October 10th.
That's Michael.
Oh, I forgot to point out zonal asymmetries. Here's a little bit. Here's some, maybe here and here. It's nice and visible to get either a sunrise or sunset, then you can see the tops of the clouds that poke up, and you can get a feel for it. If it's middle of the day and you're in the visible, it looks like just a huge white shield, sort of axisymmetric. But more often than not, my impression is that there are embedded asymmetries, such as if you look in infrared, or especially if you look in radar, or if you look at numerical models, you can see these zonal asymmetries. Here's one, a little bit here. Are they important? Do they materially affect the growth of the storm? Do they retard the storm's growth? Do they change the direction? Do they accelerate the storm's growth? Part of what I'll try to describe leads to the conclusion that perhaps these elements are accelerating the storm. I'll describe why, but I am naive about tropical cyclones, and so maybe by having growth out in here, it retards things in here and inhibits the growth. It's probably a nonlinear problem. At least it seems worthwhile to try to consider, what do axisymmetric, zonally, or radially, azimuthal symmetries, how important are they? That's the question. All right, so here's the original theory of updraft tilting of horizontal vorticity, and Shanghan and Gray just posed some shear and then had an updraft in it, and I'll show you that picture. The reason why I add this idea of large-scale horizontal vorticity is, where did this pre-existing shear come from? Well, it's the entire storm's dynamics. Where's the water vapor being ingested? Where's the latent heat release? in the growth of the mid-latitude cyclone or tropical cyclone, you'll produce large-scale horizontal vorticity because you have vertical shear associated with the storm itself. Applied mathematics studies also focused on generating gravity waves through the adjustment process. So here's Chris Snyder et al. Sort of kicking this all off. But in 2007, they initialized what they call a balanced dipole, a counter-rotating pair of vortices, which always has a jetlet in between. And this is after 20 days or so, probably non-dimensional days. And if you take a slice through here, well, let's see. This one goes this way. So the jetlet is going to be directed this direction. If you take a slice like this, you can see there's a downdraft and updraft. It's a really important pattern. And then there's this set of gravity waves. It's like a bow wave. And we can take and expand that. This is divergence, convergence, divergence. So this is a nice set of gravity waves being radiated from this dipole in some sort of adjustment process, geostrophic adjustment. It's a bit reminiscent of the classical Rossby problem of throwing a stone into a rotating ocean and seeing what you get. Gravity waves do the adjustment. Here's some work by Leslie Smith and Sam Stegman that you probably know, and postdoc Gerardo Hernandez-Dueñas. And they found that quasi-geostrophic dipoles just kind of track along, but if you add -1 rho bar g, if you include buoyancy, that's Gusenesque, then it turns to the left. I asked Leslie Smith, why does it do that? She said, I don't know, but it's sort of fun, like a caterpillar or something. This one is negative, and it can be inertially unstable if it crosses the threshold of bigger than 2F. So that just depends on what the scale is, because dV, dx, ddy depend on 1/L. If you have a small enough scale, you'll get inertial instability. Here's another view of a PV dipole, and here is ascent and this is descent. So what I'll argue later is that these idealized studies show that you have very deep vertical structures and that they're intimately related to the gravity wave field that's generated.
Is there, these just dipoles, there's no other ambient flow?
You know, I need to really dig into these papers to figure out how do they initialize these vortices, and if they're really balanced, why do they have to adjust and radiate? Is that kind of what you're thinking?
Yeah, but also just the distribution of vertical motion is not obvious to me why you...
No, it isn't. Yeah, I guess I better really read those papers carefully and learn more about that. For the purposes here, I was sort of taking qualitative analogs with what seems to be happening in reality. They're really pronounced. So they start with these, and then they get all this vertical motion stuff out of it. What happens, I think, in reality is you have an updraft, and that kicks everything off. All right, here's Shannon and Gray's now probably fairly famous paper from 2009, where, just ignore this X and Y, let's call that Y, and this is X if you want, for purposes of the tilting twisting term. These arrows indicate the direction of shear, so imagine northward flow that is zero at the surface and increases upward. Then you impose an updraft. They say, if you consider this part where B goes like W, B is the rate of heating that peaks in the mid-troposphere. This part is the vortex stretching in the lower troposphere causing PV positive. And in the upper troposphere where B decreases upward, that causes vortex compression and generates negative Q. But this picture is about the second term, which is a tilting twisting term. Gamma goes like dV dz, so that's the shear. And then d by dx of B goes like d by dx of W. So that's a tilting twisting term in Holton's fundamental textbook. So what happens is you have, if the shear is that way, then you have vorticity pointed in this direction. And so an updraft will tilt this side of it upward and you get a positive PV anomaly. And on the other side, the updraft tilts the horizontal PV downward and you get a negative anomaly. And in their case, they have very simple geometry, linear shear plus one updraft, and they find this PV dipole. You take a slicing level throughout this that you have a PV dipole. This doesn't really look like what we see in numerical models or observations. In fact, there's a really sharp concentration of a PV dipole at the tropopause level, and it doesn't really look like this. And mid-tropospheric PV sometimes has dipoles, sometimes not. It's really complicated. So this goes a certain distance toward explaining what we see in models and observations, but the question remains, why is it concentrated near the tropopause?
Okay. So going back to the earlier slide, you said that this figure is largely dominated by the second term on the right-hand side, the lambda ds.
Yes. Yeah, so without the updraft, there's no PV anomalies, and there's horizontal vorticity oriented this way.
Right.
So there's a sheet of vorticity, and then you poke through it, and you just bend it up like a horseshoe.
Right. So I get that, but I'm wondering if you were to include a jump in stratification, like a tropopause, could that?
Yes, my hunch is, and last night I thought I really better look up to see what the vertical profile basic state was. If there was no jump, then that accounts for this. If there is a jump, then why isn't it enhanced there?
Right.
Yeah, you're right. Good one. Have to check that out. About the fundamental posing of the problem. You're right. So, in trying to understand the mid-latitude cyclone Super Tuesday storm of February 2008, we were thinking, well, there's a northward shear, and from the right-hand rule, that means we have vorticity directed in the -x direction, so zeta 1 is negative. So we have sheets of horizontal vorticity pointed toward the west. And then if we impose one updraft here, it'll tilt one of these vortex tubes upwards, so you'll have a projection into the vertical component, component 3. So zeta 3 is positive here, tilting upward. Well, that's the right-hand rule. But then this side is tipped downward, so we have a negative relative vorticity anomaly. And this is a PV dipole. And if you consider that the shear is that way, the low PV lies to the left, sort of analogous to V Below's law.
But isn't that a vorticity dipole and not a PV
It is.
dipole?
It is, absolutely. So here's the next slide, which talks about that. So the negative member, if it's strong enough, it becomes inertially unstable. And the classical distinguisher of inertial instability is if this term is negative, if the minus sign will be positive. So any northward displacement will accelerate, any southward displacement will accelerate. So that requires negative absolute vorticity in the northern hemisphere, or positive in the southern hemisphere. If you look at potential vorticity, F times PV, forget the F here, PV has 1/√d theta dz, so this is an amplifier, but at the tropopause, it's positive definite, 1/√d theta dz. So if you know the sign of absolute vorticity, F plus zeta, then that tells you the sign of PV in the UTLS. It's just magnified by that prefactor. Don't really need to worry about the equivalent potential temperature because it's so dry there. Okay, so the signature of inertial instability is absolute vorticity negative. Zeta has to be bigger than -2F. Or potential vorticity negative, which is the same thing. Zeta has to be bigger than -2F. You can also get that in convection if d theta dz is negative. But at the tropopause, that doesn't happen. So what does this imply? If you have inertial instability, when air enters the region, it can accelerate. So it can create regions of enhanced divergence, and then one would expect greater upwelling and enhanced precipitation, and also gravity wave excitation. So enhanced precipitation, this goes back to the theory of symmetric instability, that many rain bands and severe precipitation events have been well understood for quite some time to be related to what we call symmetric instability, a combination of F plus zeta negative and d theta dz negative. And then this ties in with the applied mathematical studies that I just showed a couple of examples. All right, so we already covered this one. So let's go to a tropical cyclone example. And again, the low pressure center is here, and we know there's cyclonic flow this way. But to get to this level, which is at 16.5 kilometers, we know that the flow is going to start to go anticyclonic. So the shear is this direction. And again, the low PV lies to the left of the shear. Let's see if we can do that from this point of view. So here is the northward cyclonic flow, which diminishes upward. Oh, that means with the right-hand rule, now the vorticity is directed radially outward, so in that direction. And if the vorticity is directed radially outward and you have an updraft tilting it, this one will become positive on the inside, and this one will be negative on the outside. Well, that's true. This is lying radially outward, and the shear is that way. It's to the left of the shear. So this rule seems to work for tropical cyclones as well. Let's check a few other ones. This is tropical cyclone Bonnie in August of '98, and at 1640 on the 25th of August, I wish it were 23rd, all of them 23rd, but they're not. Here's a PV dipole. The low member lies radially outward, values of about plus or minus 10. Here's kind of a PV dipole. This one's a pretty big patch of negative PV. We'll talk about that in a second. Here's a positive. Again, the negative member lies radially outward, or to the left of the shear, which is anticyclonic in the upper troposphere. And then this is the wind vector pattern that goes along with that. And you can see that, well, there's a little maybe circulation associated with the positive anomalies, but pretty modest compared to, look at this jetlet that's straight away from the center of the cyclone and just spews out. So this really harkens back to the theory of Mesikowski and Tripoli, that if you have weak inertial, or maybe even, was it 1984, Robert Merrill might have mentioned this too, that if you have weak inertial stability or negative inertial stability, then the outflow can just speed out of the hurricane and maybe accentuating the vertical motions and enhancing the hurricane, or changing it somehow. Here's another example from Earl. PV dipole, -1 outward, -1 outward, -1 outward. There, this is outward. It's a lot bigger than that one. And look at this huge entire hemisphere. The entire equatorward half of Earl is just spewing in or out around. So this is compatible with the idea that inertial instability can facilitate horizontal acceleration relative to if you're in a cyclonic member of the PV dipole. All right, so try to do a general diagram for both the northern and southern hemisphere for the orientation of these dipoles based on this tilting of vorticity theory. So this is tilting of horizontal vorticity, and the purple arrows are directed radially outward. If you have shear in this direction, the upper tropospheric shear is anticyclonic, indicated by the green arrows, then we have radially outward directed vorticity. So if you have an updraft here, it'll tilt this downward, so you have the negative member lying radially outward. And this one's tipped upward, so it's a positive member of the PV dipole. And I just put a couple in. In the southern hemisphere, you have the same relationship, which is the upper tropospheric shear goes from cyclonic in mid-troposphere to anticyclonic in the upper troposphere, which is this direction. And then that means you have vorticity that's pointed radially inward, horizontally. And if you have an updraft here, it'll tip this one up and be positive, and that one negative. Ooh, is this okay? Well, the negative member does lie to the left of the shear, just like here. The negative member lies to the left of the shear. But this is the southern hemisphere. And do we have a problem that the positive member lies radially outward? No, it's the inertially unstable one. In the southern hemisphere, positive PV is inertially unstable. So this is unstable, that's unstable. This is unstable, that's unstable. It's all good. The low PV member lies to the left of the shear, and the unstable member lies radially outward. So that seems like a fairly useful universality. But near the end of this talk, I'm going to show you a diagram similar to this, which is, I think, a lot more simple and easy to understand. All right, so a series of tropical cyclones. This, oh no, sorry. This, first of all, a mid-latitude cyclone. This is our Super Tuesday storm, where 1,000 cars are trapped on I-90 overnight with a 20-inch snowfall. A lot of tornado deaths, so 78 of them. I'm going to talk a little bit about ST and jet flare-ups, just a brief comment. So we talked about this again. Here's the updrafts, and to the left of the shear we see low PV. This is theta dipole. You have a chain of turrets, and the air kind of goes around it and over it and then down behind it. So here's the PV anomaly, and check this out. So the wind shear obviously is this direction, but this is a negative PV anomaly, which means we have anticyclonic circulation. So the jetlet is pointed that way. It's pointed opposite to the basic state flow, this way. Well, you can see in this portion of the state, right in here, that the flow is diminished by this opposing jetlet. That's weird. And then over here, where it's inertially unstable, it's kind of concentrated flow accelerating forward. Okay. It's mid-latitude cyclone. Just a brief digression. If you do have inertial instability, then this is positive on the right. So that means the pressure gradient force is winning. So you have acceleration down the gradient, but then a V spins up and the Coriolis torque will turn to the right. So if the flow were geostrophic, it would be through here. But if it's inertially unstable, it'll tend to displace the jet poleward, and we could call that a jet flare-up. That may or may not be helpful for sort of nowcasting. And then if you do have an inertially unstable surge of upper tropospheric air, it can go over stratospheric air and create a fold. But this isn't actually happening in the plane like this. It's more subtle and perhaps more interesting, where if this flow is happening in the upper troposphere, well, it's quasi-isentropic, this flow. It doesn't really change its theta level very much. This is at a higher level, and if you have inertial instability and the flow surges poleward, it can just ride up and over it at about constant theta, so it's just going like this, well, like that. And that causes a fold. You can call those overfolds. All right, getting back to PV dipoles. I'd like to show a movie of how gravity waves are excited. You've seen this one before, but the rest of these movies you haven't. All right, so that's the subpolar jet and the subtropical jet. They don't really merge, but these individual blue elements are inertially unstable air masses, and you can see these sort of rib-like structures. These are gravity waves with phase surfaces that can join the two jets, and they travel upstream, similar to the theory of Bouchard.
What are the blue isoplates?
Okay, so this is a 35 meter per second isosurface. So everywhere inside this surface, the wind speed is higher than that. So this is subtropical jet and the subpolar jet. They look like they join, but they don't really. These are regions of potential vorticity less than -1 PV unit. And these gravity waves seem to have their base in the location of these inertially unstable regions. Each individual wave seems to be linked to one of these rising blobs of negative PV. So that's just the connection with gravity waves from mid-latitudes. I'll show one for Hurricane Earl that's similar for radiating gravity waves for tropical cyclones. All right, so now some tropical cyclones. This is Talus, and from September 2nd through 4th, it really harassed southern Japan. Here's the Kiai Peninsula right here, and they got 2 feet of rain, a lot of mudslides, and some drownings. This is a pretty severe storm. Here's the low pressure center on September 3rd around local midnight. And this is a infrared picture showing a pretty strong thunderstorm complex right here that coincided with the rain event. And it's even starting to show up in high-resolution ECMWF analyses. This happens to be at 0.14 degrees or 14-kilometer resolution. And you can see some PV dipole suggestion of a PV dipole that's a little bit stronger over here in this quadrant, although the UW-AOS does better at it, even after integrating for 24 hours. It's encouraging that the negative member lies radially outward in these ECMWF analyses. So a little while later, at 2100, you can see the blue wind vectors are in UTLS, the anticyclonic outflow. And here's the convective complex, really fierce. This thing lasted like 12 hours. And it's a potent azimuthal asymmetry. So here's the dipole again, and I put a shear vector on there. We'll look at profiles in a minute. But here's the updraft, and yeah, low PV lies radially outward and to the left of the wind shear. Here's a profile through the updraft, and we can see in potential vorticity, not much, but then this big spike of positive PV, 70 PV units. That's crazy. Look, this is a mistake, right? So that's what I kept thinking. Maybe it was just a horrible mistake. But it isn't. It shows up in other measures and auxiliary data. Here's the northward flow, or the cyclonic flow to the east of the low. And it's deep. For a well-developed tropical cyclone, the wind maximum isn't at the top of the boundary layer. It's 5 or 6 kilometers altitude. It's very deep. This is right next to it in the negative PV anomaly. You can see minus 50 PV units for the negative anomaly. It's offset by 20 or so because F is not negligible. So here's the wind spewing out of the negative anomaly dominates because it's inertially unstable, most likely, but that's something that we're going to check systematically across a wide range of cyclones. We've looked at about 15 so far. All right. Here's a nice little sequence which highlights one of the main points of the talk, which is in these thunderstorm complexes, these azimuthal asymmetries, they generally tilt pretty substantially, and quite often they tilt forward and actually join with the subtropical westerly jet. So here's some 24-hour trajectories. It actually takes a long time for like a low pressure center with a Rossby radius of deformation of 500 kilometers going 10 meters per second. Takes many days to go around. Parcels probably don't ever really go around that low, do they? They do something, they could park way and do something else, probably. Anyway, some of these went right up in the thunderstorm and then out, and they had a cyclonic flow. If you look at this from a little bit south of east and a little bit elevated angle, you can see for 2-hour trajectories, they go in and then up at this tilted angle and then out. Usually there's kind of an overshoot and a slumping. This is a hint of the subtropical westerly jet. So the silver is an isosurface of 34 meters per second total wind speed. It includes U, it's U squared plus V squared plus W squared square root, but W peaks at about 5 meters per second at the most, and so it's really controlled by the horizontal wind speed. How much is this tilt? Does it tilt substantially? And near the end of this talk, I'd like to suggest that our points of view about angles of tilted updrafts are really, I don't know, I think we should think about it more carefully. I'll show you what I mean after a bit. So if you take a slice along this meridian, then you can see what's happening is there's mid-level flow coming in, and this is northward flow, azimuthal cyclonic flow. But then when it gets to the updraft, it gets shunted upward and then ejected once it hits the base of the stratosphere, just ejected in the UTLS in a layer that's about 6 kilometers thick, centered slightly below the tropopause. And if you look at in terms of vertical motion and PV is in black, you can see the maximum heating is here, so there's vortex stretching producing this, but then it goes away due to vortex shrinking. Here's the negative positive PV dipole, which is distinct from the stratosphere. You go down contours before you go back up. This is a negative member, and that's right at the beginning of this polar jet. So inertial instability is probably facilitating this polar flow here. All right, we'll take a couple of soundings. We'll look in the updraft and a little bit downstream of that. This actually happens to be at a 7-kilometer level. So you can find PV dipoles at 7 kilometers in the mid-troposphere, but this one happens to be due to vortex stretching. So we have a profile in the updraft here, which, first of all, in purple, it's a healthy updraft that peaks around 9 kilometers altitude and 3 meters per second. Then it goes to zero about here, and so the tropopause is at around 15 kilometers. Here's the meridional wind profile in the updraft, a nice momentum bulge centered at about 9 kilometers. Oh, sorry, that's vertical motion. This is V, so we have winds, meridional winds on the order of 25 meters per second, extending from 3 kilometers up to almost 14 kilometers. So a very deep layer of strong forward flow. Just downstream of that, not very far, the vertical motion field is all less than 0.2 meters per second. And we have very light winds, plus or minus maybe 5, 10 meters per second in the meridional wind component, but a huge bulge of poleward flow peaking at about 45 meters per second in the UTLS. Well, Shelley kindly put this sequence together, and it shows over a 2-hour period. This is the meridional wind profile in the updraft, and this is kind of following the motion a little bit out ahead of the updraft until you get to the outflow jet. And you can see the gradual rise of this momentum bulge. And if you compare that with typical vertical motions of 2 meters per second, you can go about 7 kilometers upward in an hour, and that's about the angle of that slope. It's also interesting that the vertical motion field tends to maximize roughly where V does, so the ratio of V over W stays sort of constant through the ascent. All right, let's try Hurricane Edward. Oh, yeah, no movie yet. Okay, Hurricane Edward. It had a long history, so it gradually grew into a Category 3 and then waned again, and we're looking at it right before it reaches its maximum. At this particular time, on the 17th of September, there was a little convective complex a little bit to the east of the low. And again, we see the same sort of signature that in 2-hour trajectories, air goes around the low and then abruptly up in this deep updraft, tilting forward, and it's ejected right into this exotropical, subtropical westerly jet. Subtropical westerly jet. So there's a coincidence of the updraft with the horizontal speed maximum. And this was curious, because I always thought, well, if you have shear, and here was the lifting condensation level, and you have a cloud going up, it's going to probably slow the flow down a lot by mixing low momentum air from the gondola area in with everything else. That's sort of the paradigm that's been present since the 50s. And near the end, I'll show some pictures of Malchus's work on that. But this is different. The speed maximum is inside the cloud. It's coincident with the updraft. It's moving faster than its surroundings. The air inside this is moving faster than its surroundings. Oh, what about this right-hand picture? All right, so here's PV maximum from vortex stretching. Here's a PV dipole. You know, it's not slicing exactly through it, but there's a hint of it. This is the updraft, and then we have downdraft, updraft, downdraft, updraft. So we're rating the gravity wave pattern from this nexus right at the top of the updraft. And then if we look at profiles of wind in the updraft versus downstream in the outflow jet, here's the updraft, peaking at about 5 meters per second and 7 kilometers altitude for Earl. And then, I'm sorry, Edward. And then here's the Meridian flow, reaching 35 meters per second at about 7 kilometers. So you can see the ratio of this to this profile is roughly constant. So you might not have to have an updraft that goes tilting this way and then that way and sort of snake shaped. It might just be a nice linear profile because these two scale together. But now let's go just 100 kilometers downstream, and the vertical motion field is all less than 1 meter per second. And there's no big bulge of momentum in mid-troposphere. Instead, it's situated right here underneath the tropopods in about a 6-kilometer layer. And again, if you do kind of a quasi-Lagrangian tracing of this event, the momentum bulge that goes through starts at mid-levels, rises up in the updraft, and then gets ejected out the top. It can't go into the stratosphere, so it's almost deflected into the horizontal and sharpened and accelerated. An attempt to try to understand it. So I said, hey, Shelley, can you plot V times W? We haven't sorted out the code and interior of the code to do some Fortran and sort out W prime, V prime. But in this domain, the average W is 0 and average V is about 0 also. And so this product VW is approximately V prime W prime. And this is just in the plane, and we can see values of 70 meters squared per second. Here's minus 10, so if we go upward minus 80 in these units and take minus d by dz at that, it suggests that this momentum flux convergence could support a 1 meter per second per minute acceleration. That's coincident with the inertial unstable member of the PV dipole, which facilitates acceleration also. Not sure what the best perspective is on this. If you just have a numerical model, it all does it all by itself, and it's convection and diffusion. You don't calculate momentum flux convergences because you don't have a scale separation in the model. A long time ago, when you had poor resolution, people used to play this game. What is cumulus friction, right? If you know you have substrate scale cumulus clouds, what is the effect on the large scale grid point values? That's a different problem if you have a clear scale separation. And so that paradigm is sort of underlying why I would calculate something like this. It's sort of a heuristic argument that suggests, well, yeah, you could have pretty good acceleration there if you have a momentum flux convergence. All right, let's look at this simulation of Edward. I have two versions. These are movies from the west looking at meridional sections. And the first one has an isosurface in orange for the vertical motion field, 3 meters per second, so pretty good updraft. And then the yellow is the speed isosurface of 33 meters per second. And in addition, there will be contours of vertical motion, so we can see a lot of things in this film. The second one is isolating wind vectors in the meridional plane, and it's a little bit of a zoom in, so let's try these. All right, so here's the subtropical westerly jet isosurface around 30 meters per second. Here's an updraft of 3 meters per second. It's coincident with the yellow, which is 30 meters per second speed. And we're starting to generate gravity waves. This updraft has this phase orientation. And then there's another angled one, which is a downdraft, and then an updraft and a downdraft. So we're radiating gravity waves by punching into the stratosphere. And then this whole thing just surges forward and joins with the subtropical westerly jet. And so it kind of overshoots and then subsides. So maybe I'll just let it run for a few times. And I was really struck by this. It just sort of looks like a snake that has ingested some sort of large mammal, you know, like
What's the time scale for this animation?
The time scale of evolution of this is about 2 hours. So we can look up here. So it goes, well, wait. The whole thing is almost 24 hours. But from here to here is a few hours. Some people say that 15% of gravity waves in the tropics are radiated from tropical cyclones that get into the stratosphere, and that some 10 to 20% of water vapor that gets into the stratosphere is in association with tropical cyclones. And you can see that maybe that's true. Like, what's happening right here? You know, it's just, and then all the high water vapor air in the boundary layer is injected right into the adjacent subtropical stratosphere. Let's try this other one. So this is Edouard. 35 meters per second speed in this green color, and then these are just wind vectors in the meridional plane, V and W. So again, air is ingested at mid-level, shunted upward, and ejected out the top. I was thinking in terms of some sort of hydraulic jump analogy, but I can't wrap my head around it yet. Maybe there is one. All right. Get back to the PowerPoint. So here's just a plan view of Edouard, and we tried pretty hard to look at coincident drop signs. We have a bunch of other data sets that we want to look at to verify these features. This particular point was about in here. I should have put that marker on there. This is just a speed isosurface of 35 meters per second. So here's the outflow jet between the PV dipole. It's actually not oriented this way. It's just going forward, just completely up the pressure gradient. But it's so powerful, it's just overwhelming everything. And we can see in the drop sign that the zonal flows are about 12 and meridian about 22 meters per second. So right there in the outflow jet. Good, a little confirmation anyway. Very, very hard game to try to match dropsons with features in mesoscale models. They're never where you want them. It's a time-space problem. Okay, this one is tropical cyclone Ida. So let's test our ideas for the southern hemisphere. It recurved this way into the southern hemisphere subtropical westerly jet. And around the 10th of April of that year, we can see tropical cyclone Ida. Right in here, there's some nice convective complexes that you can't necessarily tell from this picture. It's right over in here, and BCMWF data. All right, so southern hemisphere, low pressure here. We know that in mid-levels, air is coming around this way, so that's cyclonic. And in the upper troposphere, it reverses to anticyclonic, so the upper tropospheric wind shear is this direction, and low PV lies to the left. Good. But look, there's more flow associated with this positive member, it lies radially outward. Oh, it's okay. It's a positive PV is inertially unstable in the southern hemisphere, so it all works according to these mnemonic rules. Not mnemonic, just rules of thumb. All right, so here's Ida. If we're looking from the northeast, we can see the same thing. Air is ingested into the updraft, and it has a little overshoot, and then it hits right into the subtropical westerly jet. It's just remarkable. So here's the PV dipole in blue, and here's the updraft, and here's the downdraft, and this is the poleward outflow jet between the two. And so if we take, I'll show profiles in the updraft and downdraft in just a second. But before we do that, let's look at this slice where this is southward, so it's going that way. So this is toward the South Pole. Air comes in at low and mid tropospheric levels, is shunted upward and then ejected in the upper 6 kilometers of the troposphere into the stratosphere. Here's negative PV. Well, that's all right. The stratosphere has negative PV, F is negative. Here's inertially unstable air, which helps accelerate the flow that way. And here's an updraft of 5 meters per second. So in the updraft, again, we have a nice maximum and upward motion of 5 meters per second. And here's the southward momentum surge, which is very, very deep. But when it gets ingested in this updraft, it is ejected out the top toward the South Pole 6 kilometers later in the upper troposphere, lower stratosphere. The same thing as the other two cyclones and their PV dipoles. All right, so can the form of UTLS PV dipole jetlets be predicted? Okay, so this is the part that I'm most happy with. Somehow in the middle of summer, I finally figured this out. All right, so in mid-latitudes, we have very deep shear, and here's the tropopause. So you might have some ascending updraft that carries momentum upward that's a little less than the ambient momentum. And so this is the sense of the jetlet between the PV dipole. And the UTLS jetlet that would form from detraining this momentum into this ambient air would be a negative jet. Well, that's what we found. We have a negative jet here, and the air goes around this way. All right. So the jetlet opposes the basic state flow in the mid-troposphere for mid-latitude cyclones in general. What about this paradigm? In tropical cyclones, you have cyclonic flow, and if it's in an updraft that carries it into the tropopause region, into the UTLS, it'll be going way faster than the anti-cyclonic flow. In fact, you'll create a jetlet like that. So if you take this prograde jet in the sense of the mid-tropospheric cyclonic flow, it's this direction. Well, that means that the negative member is to the right of that. That's the opposite of mid-latitudes. And it's because this flow is faster than the ambient flow in the UTLS. The third option is, here's the third option. No momentum difference between horizontal speed in the updraft and the horizontal speed in the UTLS predicts no UTLS jetlet and no PV dipole. This is the idea that the jetlet is most fundamentally, intuitively, the thing to think about first. If you simply put air that's moving at different speed abruptly here compared to the surrounding air, you're going to get a jetlet. And if you have a jetlet, you'll have a PV dipole. But if you don't have wind shear, you won't get one. That's the prediction. So, all right, here's the two perspectives on where the negative member ought to lie. We'll just concentrate on the northern hemisphere. This is the point of view that I said before. If you have upper tropospheric anticyclonic shear, then the horizontal vorticity is radially outward. And so if you tilt it with an updraft, it'll go down on the outside and up on the inside. All right? But what if we use this new perspective, which I think is simpler and more clear? But let's remember what the mid-tropospheric flow is. So these green arrows in this diagram are the mid-tropospheric cyclonic flow. That means if you pop some of this up to the upper troposphere, you'll have a jet in the same sense, and therefore a negative member lying radially outward. I prefer this point of view. It's sort of more physical and intuitive than dVdz times dWdx with a minus sign. All right, so we can check on the predictability of forms. You might like these. This is revisiting the Wisconsin flooding events where there were two 15-inch rainfall events, one in Black Earth on the 20th and then Baraboo Hills on the 27th. The first one we're predicting with no shear, no jetlet. The second one, we're predicting reverse jetlets in northeastward shear based on these rules. All right, so here's the precipitation anomaly that led to waters rising above the bridges and floating them and displacing them and putting large mats of islands of vegetation on top. It was really intense. I wish I were there at 9 p.m. on August 21st. It would have been incredible. I probably would have gotten swept away and drowned, caught in a barbed wire fence a mile downstream. Bad news. Okay. I don't think they fixed this bridge yet for Highway 14. A lot of rain. All right, so here's the still shot for the first storm. This is a remnant of the PV stalactite. It's a wrapped up vortex detraining from the base of the stratosphere. And the convection just destroyed it. And it left a large region of negative inertial stability, which facilitated precipitation. Getting close to being done here. All right, so let's look at the Wisconsin flooding event. Here's the PV stalactite. Look at these updrafts and PV anomalies just completely destroyed it. It's sort of astonishing signatures. Somebody should maybe investigate that further. And then this residual of all the convection is just sort of a negative inertial stability regions, inertial and unstable, that probably through symmetric instability help facilitate the rain bands. They're never in the same place as the model exactly, but qualitatively somewhat similar. Here's the one 7 days later, and this is just to verify that if you have strong shear this direction, then you can see these PV dipoles erupting that are low PV to the left. And if you think about it, this is cyclonic, so the jetlet's that way and it's opposing flow because you're injecting mid-tropospheric air into the UTLS, which is moving faster toward the northeast. All right. And this confirms that on the 20th, that wind shear up to the tropos was fairly mild, but it was quite deep and it went a little past the tropopause, and 7 days later it was a taller, deeper troposphere. All right, I guess I have 1 minute to show a few of these. Examples of shear convection. I just want to raise these questions for you to see what you think about. Because when I started to think about tilted updrafts and tilted trajectories and trying to disentangle it, it became kind of an adventure. I got to look back through all this literature on convection. So some questions are, what are typical aspect ratios of deep convection? I'll tell you, I think they're like 10 kilometers by 10 kilometers. They're blocks. Are they towers? Are they really towers? Well, I suppose they're hot towers, I guess, but not necessarily towers. Are they vertical towers? Who knows? There's vorticity associated with them, but if you look at any particular updraft and color code it with the updrafts or isosurface with PV, you can have almost any pattern you want. So yeah, you can say vertical tower, but what kind of vortex? The only thing that's meaningful after looking at this is UTLS PV dipoles are robust. Maybe you can talk about hot towers and PV dipoles. That would make sense. But vertical hot tower is like saying, I don't know, it's like saying cows with 4 legs or something. Right? I don't know. It's just, I just failed to grasp the meaning of it. Well, some Castellanos are pretty tall, I have to admit that. But this isn't the typical shape of a thunderstorm. It's like 20 kilometers wide and 15 kilometers deep. It's probably wider than it is tall. Here's one, I guess, not much shear. It's almost like a random walk. The individual turbulence elements sort of take them in somewhat different directions. A little bit of shear. You probably use this yourself. It's calm outside. What's the wind direction aloft? You take a glance and you can tell it's going that way. Probably some shear that way. And wow. I think this was from Lee Orff's run of October 31st, 2017. I don't know what it is. Pretty amazing model he's got. This is almost like from an artist depiction in France or in Japan of countrysides, but this nice shearing of these cumulus elements. That looks like about a 45-degree angle. Here's Joanne Malkus's early work in the 52. She was trying to come up with a formula for how these should be tilted. This is interesting. An equation for the slope is derived. It's shown to be dependent upon the vertical ascent rate, the external wind shear, and the horizontal friction forces. The frictional forces are 2 origins, one due to entrainment or mixing, and the other due to former body drag. That hasn't changed. She was right. If you look through the literature thread on that, she was right about it. Here's another version, she says that the flow in the surface is going to the left with the flow aloft being not moving very much. I'm not sure if that's true, but here's the crux of the strangeness of this. All right, so if you have an updraft W that's a comparable speed to the horizontal motion, then particles and the updraft will have this tilt. Even if this maximizes in the mid-troposphere, so does that. So the ratio is a constant, and so you get a roughly constant tilt. That's 45 degrees. Some of those pictures look that way, but that's not really the way things are. We usually have horizontal speeds that are 20, 30 times bigger than vertical motion. So a typical angle for an updraft would actually be 87 degrees, which would be plotted like that. Is that what it looks like? If you could take away all the darkness and all the other clouds and just isolate one updraft in a hurricane, does it look like that? What do you think? What we really do, though, is if we represent this to be 1,000 kilometers and this to be 10 kilometers in a typical aspect ratio for an image, then this one is collapsed to here. Although that looks like a tower. And this one is collapsed to here. Ah, it's just tilted off the vertical by 11 degrees. It's slightly tilted. But in physical space, it's actually like that. Isn't this true?
Don't you have to have the convection being infected with the wind?
Well,
I mean, those,
so,
particularly in a hurricane, they're
yes.
being infected. So
Yes, but well, in a hurricane, what I would argue is that crossing the isobars and the buoyant acceleration accelerates U, V, and W so that it's going faster in the cloud than the surroundings in a hurricane. It was really, when I realized that, that's completely the opposite of what I ever thought before. Yeah, so typical map scaling is 800 kilometers this way, 16 kilometers that way, like a 50 to 1 stretch. Ooh, let's try it. All right, let's stretch this sucker. That's still not 50 to 1. Anyway, we're getting close to what physical reality is. It's actually tilted way over more. So this says that trajectories and the updraft are coincident and tilted way over in real physical space. And that all along we've been deluding ourselves and thinking that it's almost upright because of our aspect ratio for the maps that we use. I mean to be provocative. All right, I'm done here, just a sec. Theory of convective momentum transport. All right, so Malthus is right. If you can figure out a coefficient to relate turbulent entrainment, if the wind inside the updraft is faster than the air around it, it's going to speed up the air around it. From the form drag, if the wind is faster in the updraft than the air around it, you're going to speed up the air around it, so both of those act in concert. Some people choose CD to be about 0.5. Another thing is that a PV dipole is a big stirring agent. You get KYYs on the order of 1 million to 10 million meters squared per second. So a vigorous mixing agent distributing material into the stratosphere. The last thing, I can't help it. So this is rho prime. It's the departure from the domain average of profile of rho. So it decreases into this updraft, and then it decreases up to here, but it increases up to here because you have to have a deceleration, and then it's shunted that way. So this gives me, this emboldens me to propose a naive view of how momentum surges work. The double dot is called a diuresis. I just looked that up. But maybe it's like two eyes, like that little kid in the emperor's clothes. If you're really naive, maybe you can see things more clearly sometimes. What about this pathetically minimalist point of view? The high humanity gathered inward and upward leads to an inward and upward decrease in density anomaly. And it's true, there's an equation of the time rate of change of sea level pressure drop is equal to the vertical integral of the time rate of change of density. Okay? Hence an inward and upward PGF that's strong, resulting in acceleration of both the horizontal and vertical winds, such that the air in the updraft has a higher horizontal speed than the surrounding air. All right, finally, conclusions. I went on a little far longer than I thought. So, a typical situation is cross-Cyclones flow injected into the updraft where it's accelerating because of buoyancy, hits the stratosphere, makes a PV dipole, and is ejected poleward. So, I think we finally understand the location of UTLS PV dipoles is determined by the stratospheric stability stops the updraft, and there's a confinement of the outflow. It's a deflection. The updraft tilting of large-scale vorticity correctly predicts low PV lies to the left of wind shear and anomalous PV lies radiated outward in TCs, but the theory of momentum difference predicts the confinement and the orientation of the mid-level flow relative to the PV dipole. In mid-latitude cyclones where the poleward speed of the updraft is less than UTLS, the jetlet will be negative, but directed opposite to the flow, and low PV will lie to the left of the updraft horizontal wind. But in tropical cyclones, where the cyclonic speed of the updraft exceeds that in the UTLS wind, the jetlet will be positive, and the low PV will lie to the right of the updraft horizontal wind. This all seems to be borne out in observations. And lastly, zonally asymmetric convective complex are good at transporting moisture and momentum and other things into the stratosphere, and they may affect tropical cyclone growth and storm track. And I admit to being naive, I can't really foresee where that part's going to go, but maybe we'll get the chance to look into it. So this is in the middle of revising this one, and it's actually been helpful to give this talk because it really clarified ideas, and I think I'll be able to deal with the reviewers in a better fashion. All right. Thank you for coming on such a nice sunny day, and hopefully it was amusing or interesting.
So you're saying the primary source of the PV dipole is momentum transport?
I think so. That you make a jetlet, and therefore a dipole, but it's really large amplitude because of the d theta dz right there.
So
it's a big jump in theta.
So you're bringing up both positive and negative potential vorticity.
No, I'm saying it's created in situ by the momentum surge.
So there's a generation of potential vorticity mechanism.
It generates absolute vorticity in a model or in a diagnostic situation. And then if you simply multiply it by 1/ρ of d theta dz,
but how does it create, I mean, in the outflow trajectories, you have the trajectory going up the eye wall and then in the outflow. Where is the potential vorticity created to give two different signs of it?
Well, so the model is not designed to conserve PV. It has equations for conserving UVW, theta, moisture, and other things. And so
but it does, but it works out that it has to conserve PV if it's correct. It would have to conserve potential vorticity unless there's a diabatic process.
That's isotropic potential.
So if you try to constrain the problem by saying potential vorticity is conserved forever and ever, you'll never get anything. You won't get anywhere. Nothing happens. Brad.
So, first of all, there is a paper, Adrian Tux on it. He flew over a tropical cyclone in '94, Glacial Mesa, and they saw tropospheric chemicals in the stratosphere. So that's certainly consistent with your trajectory.
Yeah, something about a flight over a hurricane rain band in Darwin where they went upstream and downstream of it and found some processing in the lower stratosphere for water substance.
Yeah.
Yeah.
But
maybe it was a gravity wave influence.
If you instead, you're moving this PV tube up, right? And if you looked at it isotropic potential vorticity, you would just be distorting, and the isotope would move in exactly the same way. And maybe your
that
PV
could well be.
is because you're looking at this Ertl's potential vorticity, not an isotope. And then the inertial gravity waves are really more like flow around topography, and they're being radiated away because of just that distortion of the isotope.
Well, so from the point of view of PV, I guess you can have upward advection of PV, horizontal advection, but you can have production or destruction of it by d by dz of q,
right?
And you can have production or destruction of it by the curl of the friction in the horizontal.
Right.
Those two can change PV. You're right that it's incumbent on us to try to join what we see in this perspective with PV perspective. That's true. I agree.
Very intriguing, that. I think it's really exciting. one of the things that strikes me when you went to Leslie and Sam's work, and I forget, Professor Dueño, there's an interesting couplet of vertical motion in there, and oriented, you know, if you think of the couplet, it's oriented perpendicularly to the dipole.
Yeah, I realize, I don't understand that.
Yeah, and it made me think throughout your talk, there's some larger than gravity wave scale adjustment going on here because of this weird geometry, but I can't see it in everything else you've said. So I'm wondering if, take it back to your lab, let your brain chew on that for a while, and see if there's some sort of adjustment that you might be going on the mesosynoptic scale here that is, you know, affected by the dipole presence, because it's not just one updraft, at least in the idealized model. There's an updraft, downdraft couplet in the spot where your updraft is. And that's curious.
And does that determine what the gravity wave pattern is, or is it a separate issue from the gravity?
Right, yeah, I don't know what's going on there. So that's an extra little dimension that might be worth pushing. And some of these other pieces that you've already filtered out, you've got them all together in a nice, orderly thought process, which seemed difficult.
Here's another one. I'd say
It'd be nice
every
to get a
day
couple more.
in the last week, it's like, oh my God, I think, wait, maybe it's like this.
Yeah.
I'm just gonna put that in. And then
I think it's a great example of how getting progress in science is a matter of looking at a problem like a Rubik's Cube and just turning it around. And just keep on turning it around.
Different perspectives.
Yes.
Yeah. And Greg and Brad, I do need to figure out how this relates to a classical d by t of following the motion. How does PV change? Yeah.
Sounds really interesting.
But, yeah, go ahead.
You know, one thing I was thinking is when I look at isentropic flow, you very seldom see inertial instability on an isentropic surface. But you can get inertial instability on a pressure surface. Now, what does that mean? That means that you can create wave-like disturbances along a pressure surface that the flow is not moving along, but instead it's just gravity waves. You wrinkle up the isentropic surfaces because of this inertial instability across an isentropic surface or between. And I think this is the kind of thing that would be generated by tropical cyclones. They would upwell very low potential vorticity in a field of relatively high potential vorticity, and that would initiate wave-like disturbances along a pressure surface.
I think I have the answer.
What's
I have
that?
the answer. So it is the curl of the frictional stress. So if you inject a momentum pulse right here, that is a tangential frictional stress to spin this up. That is a tangential frictional stress to spin that up.
And that's true on isentropic too.
Maybe that works.
Isentropic potential vorticity, either the vertical shear, the vertical gradient, theta dot, or the horizontal gradient of the momentum, the frictional stress.
Because you're either putting
All right.
something moving or not.
I'll add that equation, and it's already too long. Michael.
So, I mean, another way to get the horizontal dipole is through the diabatic redistribution of potential vorticity. If you have a very highly sheared flow, so if the outflow is a very thin layer that has significant vertical shear, your vorticity vector, or your vorticity vector is going to have a significant horizontal tilt. Now, this is probably truer in lower latitudes and higher latitudes because you have F there, but if you have a strong tilt to that vorticity vector, then it's not DDZ of the vorticity, it's the vorticity vector dotted with a heating gradient. So you have to have an elevated heating gradient that's along across the vorticity vector that will then give you this diabatic redistribution.
Surely diabatic heating is important for creating PV anomalies that go in the updraft, and there will be a residual of them to influence UTLS. My hunch is that the time scale for radiative heating in the upper troposphere, lower stratosphere is fairly long, so that it has something to do more with the del cross V or del cross F, the friction. Sort of.
Those overshooting tops will go into the,
Yeah.
you see them into the stratosphere.
Sorry?
So your theta dot in that deep convection is going right up to and perturbing the couple ball.
Yeah, it is.
So you do have a strong gradient of theta dot.
Okay, yeah. I thought I'd figured it out, but obviously I haven't. So this is a good opportunity for me to try to figure out your legitimate points of view and criticisms and see if I can make this work from a classical PV perspective.
I would guess that the source of the high potential vorticity is almost certainly the stratosphere. That it's folding down the stratosphere in places, and that gives you your high potential vorticity anomaly, whereas the updraft from the tropical cyclones bringing up low potential vorticity due to the loss of vertical gradient of potential temperature because it's all deposited at the same level. So I think the combination of the two creates low potential vorticity above the storm directly, and then higher potential vorticity outside that's brought down from the stratosphere.
Maybe. You really need that impact in the little jetlet to get it, though. So you're saying by hitting the stratosphere, it might dislodge a positive anomaly
Well, there's
here,
compensation.
and the residual of the vortex compression makes the negative one.
There's going to be some compensation downward from the stratosphere, which is how we get most of the high potential vorticity anomalies we see anywhere on the planet, or almost always, because something comes up from below that pushes the stratosphere down in it, and you get stratospheric injection of high potential vorticity.
The thing is that the vertical scale is the same as the outflow jet scale, and the horizontal scale is the same as the scale of the updraft.
Across the updraft, yeah, it's too small scale to. My instinct is that's too small. That's a large scale process. This is a small scale.
Well, obviously not completely solved. Yes.
This just goes back to where you're showing the radial distribution of convection and tropical cyclones and talking a bit about that banding structure. I don't know if you've looked at any of Jason Dunnion's work on the diurnal pulse.
Okay.
That has an impact on the radial distribution of those convective features on a scale of a couple of hours. So I don't know how that plays in here. That time scale might be longer than what you're looking at here, but there might be something.
There's so much literature in there that I really need to spin up on for sure. And I kind of have a little chutzpah even getting into tropical cyclones.
The other comment the other question I was going to ask was the Doppler radar data, I think, would shed some light on what you're looking at, these structures, just kind of verifying these structures in model world versus observation world. I know you looked at the dropsons, but
one dropson got lucky with.
Right. But the tail Doppler on P3 and the Eldora, which was used during T-Park in 2008, that data is a fairly rich data set showing three-dimensional wind structure in these TCs.
I really hope we get a chance to look at that sort of thing.
Yeah, and the Eldora data was really focusing on the rain bands and the structures on those TCs and Westpac, so that might help.
It would, because, I mean, it's still a little bit uneasy that, are these purely numerical artifacts? It seems not, but it would be nice to have further confirmation.
All right, let's thank Matt one more time.